All right, so welcome to Physics Sharp. We are going to talk about an electromagnetics problem today. We basically have two parallel wires which are separated by a distance of 8 millimeters, and both of them carry same current, 20 amps, but the currents are oppositely directed. So, and our goal is to determine the magnitude of the magnetic field, and the particular point where we are actually measuring this magnetic field, that point is actually exactly same distance away from those two wires, and the distance is 5 millimeters. So there are some interesting aspects of this problem. First of all, the physics is quite simple. It basically comes from our usual formula. If you have taken like an introductory college physics class or any electromagnetic class, you have seen the calculation for magnetic field at any point in space due to a current carrying conductor, and we say that that conductor is like infinite in size. In reality, it's just a long conductor. It has its own formula, which I'm going to show you later. But the more important, or rather more interesting aspect of this problem is the geometry of it. So because of having two current carrying conductors, we basically have to consider the fact that magnetic field inherently is a vector. So there must be some kind of geometrical consideration before actually finding out a magnetic field contributions from two conductors at certain point in space. So let's get started. So roughly what we are doing here is we are basically saying that the surface of this page where I'm going to work on, my workspace, is going to be exactly 90 degrees with those current carrying conductors. So the best way to implement such thing is to say that so this is one conductor going into the page, so the current in that conductor is going into the page. So that is why we take this notation like a dot and cross notation. So this cross sign means that we are we're able to see the tail of that current. So that's the cross sign there. And then the other conductor is, let's say that this is right over here, and let me try to, here. So it's a dot, and coming out, the current is coming out of that conductor. Again, these two conductors are perpendicular to the surface of this whiteboard I'm using. So obviously they are oppositely directed, and both of them have 20 amps of current. And now the other information that we're going to use right now is that this 5 millimeters distance, and this distance is between one of those, actually each of those current carrying conductor and the point in space where we're measuring the magnetic field contribution from both of those. So as you can see that this must be somewhere, I should say not somewhere on the line, the straight line that I can draw connecting these two conductors, because if it was on the line, then it has to be the midpoint, because this point is the same distance away from the two conductors. And then in that case it cannot be 5 millimeters, it must be 4 millimeters, because the distance between the two conductors is given here by these 8 millimeters. So obviously what we can say that since the distance of that particular point is 5 millimeters, not 4 millimeters, that means it's more than 4 millimeters, then we can say that roughly it would be somewhere over here. So that if we connect the midpoint of that conductor with this point where we're measuring the magnetic field, and the other conductor as well, then we basically form like a triangle thing, where let me use a different color for it, but where we are going to say that my distance between let me try. So got it. So the distance between the conductor and that point is 5 over here. The distance between both of the two conductors is is 8 millimeters. So individually, the midpoint and the center point of the conductors are 4 millimeters. And then if I kind of connect these 2 points together, let me redraw that here. So roughly, I can say that this is a right angle triangle. My drawing is not that good, but you get the idea. This is a right angle triangle where using like simple geometry, we can say that this side is 3 millimeters. Now, so what is the implication of that? We will see later. We'll see now actually. So first of all, let's imagine what would be the direction of the magnetic field that has been set up by the left conductor where the current is going into the page, the cross sign. And we're obviously measuring the magnetic field 5 millimeters away at this particular point here. So what is the magnetic field's direction at that point? Then that's the question we ask ourselves. So the easiest way to find the direction of the magnetic field here is to say that, okay, from our previous magnetic field due to current carrying conductor, we know that the magnetic field lines are going to be create a circular path around the conductor. So at any point on that circle, the actual direction of the magnetic field is going to follow a tangent line drawn at that point. And the easiest way to draw a tangent line is to draw a line exactly perpendicular to the radius of the circle. So what I mean by that is, let's just imagine that we can maybe draw a circle like this. So it's going to be like roughly a circle about this center point over here, and this purple color line, it's basically a circle that I draw at the point where I'm trying to measure the magnetic field. So the direction of the magnetic field for this current going into the page is going to be directed exactly 90 degrees or like perpendicular to the radius path, and it is going to be directed in this direction. So this arrow, this purple arrow that I just drew, is going to be the magnetic field due to the current that is going into the page. Now you can ask me, how do I know that the direction is this way and not towards the northern direction? That comes from the right hand rule. So if I point my thumb into the page, so basically if I point my thumb towards the direction of the current, then and I rotate a right hand screw, then the direction of the other 4 fingers is going to give me the direction of the magnetic field. So so this is the direction that I get using the magnetic field. Now you can verify the direction of the magnetic field at this point, but due to the other conductor, let me change the color now. It will be confusing otherwise, because we'll have like so many circles and arrows going on in there. So in the other conductor, if I draw a similar circle around it, then okay, let me try it again. Okay, that's okay. So if you imagine that this is a circle, obviously it's not, but if you imagine that this is a circle, then the direction of the magnetic field due to this current is basically going to go this way. So the only information from this that we can tell is that the angles between the radius lines and this the direction of magnetic fields are just going to be 90 degrees. So these two angles are 90 degrees. That's all we can know from this construction. And the other information that we got was the right angle triangle was a 3, 4, 5 right angle triangle. Again, that 3 we got from using simple Pythagoras theorem. It's just the hypotenuse is 5, and then one of the 2 other sides is 4, then the other one must be 3. 5 squared minus 4 squared, and then square root of that. So from that information, actually, what we can do is we can measure the angle between these two lines. So this angle, we can measure that, and we can say that on the other side we have the same angle. So the measure of these two green angles are same. Now, what is that measure of that angle? So it's just basically comes from the cosine of that angle. So cosine of that angle, or you could just use sine of that angle, doesn't matter. So cosine of that angle is just going to be, if I call that theta, then the cosine of the angle is just adjacent over hypotenuse, so it would be 3/5. So this angle theta is going to be cosine inverse of 3/5. Okay. So all in all, we just know those two angles, and we also know that the two red angles are obviously 90 degrees. But why do we need that? That's the thing. What is our goal? So see that our magnetic fields are these two guys, B1 vector and this B2 vector. So once we understand that these are the two magnetic fields that there are, being applied, and that are basically, these are the two magnetic field contributions from the two currents on that particular point in space, all we have to do is just consider these as vectors and then we add them. But the problem is that we have to compute the angles between these two vectors to actually add them, because vectors, they depend on the exact angle they're applied on. So so what we are actually looking for is this particular angle. So we don't know what this angle is. So this is what we want to know. Now, so this angle comes from the fact that the angle created at any point in space, if you take the entire angle and if it's a two-dimensional, then it always is 360 degrees. We all know that. So see that except this angle that I'm trying to find, all the other angles associated with this point are known. So cosine inverse of 3/5, and then twice of that, because we have two of those green angles, and the two red angles are 90 degrees. So you add them up and you subtract this sum from 360 degrees and you get this unknown angle. So if I call this unknown angle, let's say alpha, then I can safely say that, okay, alpha is just basically 360 degrees minus 2 times cosine inverse of 3/5, and then minus 180 degrees coming from the two 90 degrees. So basically we are adding everything up and then subtracting from 360. I used my calculator, you can verify, but the angle comes out to be cosine inverse of 3/5. If I use that, and then the angle comes out to be 73.74 degrees. So 73.74 degrees. All right, so we're in good shape now. So we know the angle between the two vectors. We're almost done. The final thing that we need to know is the actual magnitude of the two vectors, which, as I told you in the beginning of this video, comes from the formula for a current carrying conductor setting up a magnetic field, and the magnetic field formula for that current at any point in space. And that formula is, let me use a different color for from now on. That formula is basically, like, if I call that magnetic field, magnitude B, then it's equal to mu naught I over 4 pi r. So this mu naught is obviously free space permeability, which basically is a constant, 4 pi times 10 to the negative 7. I is the current. In this case, both of the two wires are carrying 20 amps of current, so we just plug that in. And then 4 pi constant, and r is the distance between the current carrying wire and the point where we're computing the magnetic field. So if I plug those numbers in, then both B1 and B2, although I called it B1 and B2, they are essentially going to be the same because they have the same distance r, same current value I 20 and 5 millimeters. If I plug those numbers in, then I end up getting 4. So what I'm doing in my calculator right now is 4 times pi times 10 to the negative 7 times 20 amps, all divided by 4 times, actually I probably wrote this wrong. It should be 2 pi, not 4 pi. So let me correct that real quick. Yeah, so the formula says 2 pi. So then, yeah, divided by 2 times pi times the distance, which is 5 millimeters, so 5 times 10 to the negative 3. So we end up getting 8 times 10 to the negative 4. 8 times 10 to the negative 4. Awesome. So that's good. So that this is in Tesla. That's the unit of magnetic field. So now we know the magnitude of those two vectors. We know the angle between the two vectors, 73.74 degrees. So the final thing to do at this point is to just add them up. And the formula for adding two vectors where the angle is known is basically, you know, if I call it like a B total, as like B subscript T, is equal to, you know, square root of B1 squared plus B2 squared plus 2 times B1 B2 times cosine of the angle between the two vectors, which we called alpha, and then the square root. So that's the formula. So now both B1 and B2 are equal to each other, which is basically B that we just computed. So plug that number in, 8 times 10 to the negative 4, and then square it, add them up, and then 2 times the same vector. So basically it's B squared again. B1 times B2 is also B squared. Times cosine alpha is just cosine 73.74 degrees. And if I do that, I end up getting, the number was, I think, 1.28 times 10 to the negative 3 Tesla. So 1.28 milli Tesla. So that's the final answer for the magnetic field for the two current carrying conductors in this particular setup. One major pitfall in this problem might be not to understand the fact that so this is kind of people usually make mistake in. So they compute these two angles quite all right. They add them up, and then they kind of imagine that, okay, so this total angle, overall angle over here, so basically like twice that theta, so that 2 times theta has to be equal to the angle over here, the angle that we are looking for. This, however, is not the case. Why? That's because you cannot guarantee for fact that the direction of this B field, direction of this B1 vector, is in the same line, same straight line as this radius line over here. That might be true for some cases, depending on the numbers we're using, but in general, it's not going to be the general case. So you cannot take that for granted, and that would trip you off in the wrong direction if you do that. So that's one thing, and it's specifically a geometric problem. Like it's an issue with the geometry, not the understanding of the physics, as I should say. So as I said, this is more like a geometry problem than a physics problem for me. If you know the formula beforehand, I'm going to provide a good website link where it talks about how you can derive this formula, this particular formula that I've been talking about, like B equals mu naught I over 2 pi r. The derivation is quite simple if you know certain laws of physics. Other than that, all you have to the major concept in this problem is to grasp the idea of vector, and to know that the magnetic fields are always vector, and also to know that the magnetic field about a current carrying conductor would always follow a circular path, so that whenever you use a right-hand rule, the direction of magnetic field at any point in space is just going to be along the perpendicular direction, a direction perpendicular to the direction of the radius vector or the radius line. All right, so thanks for watching. If you have any comments I would love to know about them. Also, you can make this problem a little more interesting, maybe by saying that, okay, so the direction, I mean the distance between the point where we're measuring the magnetic field and the current carrying conductors are not same, just like we had in this problem, like 5 millimeter. It might be like, say, 8, not 8, maybe like 7 millimeters from one conductor and like 3 millimeters from the other conductor. Can we do that? That's a sort of question that we might ask ourselves. Or we could say that, okay, so the direction of the current are not oppositely directed; they have the same direction. It would be obviously not too different from what we have in this problem, but the computation would be a little more different. Not more challenging, though. It's going to be very similar. Otherwise, what we can do is, yeah, so we can have 3 of these conductors. It's probably going to be a little more involved than what we have, but we can try them out anyway. All right, so I will post some important links where you can verify the value of the constant that I used, mu naught. So you can have a list of many different physical constants for there. It's a good website, you can visit it. And then I will have obviously the derivation of that formula, and then yeah, so until the next video, have a good luck. Thank you.